Alright, so let's pick up from last time. We were talking about how to have a Boolean variety A over K. You get a corresponding Galois action on its origin points, and this can be sort of glued together into an identic representation. If we wrote down this phi A, which is in turn made up of lots of p-adic representations, phi A, p infinity, which you can think of canonically as mapping into the automorphisms of the Tate module, which is something glued up of all the p-powered origin points. Sort of a convenient construction because it's a finite ZP module, which is, once you pick a basis, isomorphic to ZP. Okay? Okay, so it's very useful for many applications to have this representation be as large as possible. So you want large orbits of torsion points. There's one thing which comes in the way of this representation having large image, which is it has to commute with endomorphisms. Okay, so in particular, if we have AB, which are Boolean varieties over K, and suppose you have a homomorphism from A to B. So it's a group. You can think of it as a morphism of algebraic groups, or it's a group homomorphism, which is also a map of algebraic varieties, either one of these. Well then, because this map is defined over K, on sort of for every fixed n, if you map any point from here to here, then this map has to commute with the Galois action. So you can apply the Galois group here or over here, and that should commute. So putting that together formally, what you get is that if you have a map like this, and you note by psi p the induced map on Tate modules, you just get by gluing together the maps of the p-powered torsion, and you take an element v in the Tate module of A, then, let me just make sure I get this correct. So V is in the Tate module of A, and let's say G is in the Galois group of K. Then psi p, let me just write this down. Phi A, P infinity, G applied to V is equal to phi B, P infinity, G applied to psi PV. Okay, so formally, this is what's true. Again, intuitively, you can either first map it into the Tate module of B, and then apply the Galois action, or you can first apply the Galois action, then apply the module of B, and these two should commute. Okay? Okay, so in particular, if A equals B, and psi is actually an element in the endomorphisms of A, which means that Cp induces a map from TPA to itself, and that map has to commute with the entire Galois image. Okay? Which in turn means this can't be sort of as big as possible. Be a little smaller. Okay. So this turns out to be, in some sense, the only obstruction. So there's a theorem which is due to faultings. And conjectured by Tate. which says that if you assume that your field K, which so far has been arbitrary, just characteristic 0, for characteristic P, we have to avoid the characteristic prime here, because that behaves a bit differently. But let's say K is finitely generated over Q. So it's either a number field or sort of a number field with finitely many transcendental elements in it. Then, if you look at the group algebra, where you look at the image of the entire Galois group, and you allow QP-linear combinations, then this thing sits inside endomorphisms of the Tate module, and this guy here is the commutant of all the endomorphisms of A. Okay, tensored out with QP. Okay, so this is some semi-simple algebra which follows pretty easily from just the structure of Billian varieties and decomposition into sort of simple factors. And the theorem says that this is also a semi-simple algebra, and moreover, these two are exactly each other's commutants. Okay. For clarity, I'm going to put n sub k here. That's important. So we're only allowing endomorphisms defined over k. Okay. Maybe I'll just mention in words that if K is finitely generated instead of a finite field, so a finite characteristic, then you can make the analogous statement for all primes different from the characteristic, and then that's due to Tate. Somehow. Much simpler argument. Okay. So, let me mention some more work in this direction. So, this is obviously a wonderful theorem, and it's very strong. It's not quite as strong as it might be for a couple of reasons. One reason is that knowing this algebra doesn't actually tell you what this group image is. Okay? Yeah, so like maybe one example before I get to here. One example which explains that is you can take the dimension to be 1, and you can take G1 to be sort of the diagonals together with the anti-diagonals. Okay. No, it's not good. No, never mind. Okay, I can't make an example on the spot. Sorry. Okay. So one drawback is that this doesn't quite tell you what the group is. It only tells you what the algebra is. Another drawback is this is a QP linear theorem. So it doesn't tell you what the image really is. Usually it only tells you up to finite index. Okay, so for example, like SL2ZP has group algebra, the full matrix algebra. But so does any finite index subgroup of SL2ZP. Okay, and this really matters when you want global theorems because you want some sort of uniformity over P. Okay? So, an example where this has been achieved is in the famous theorem of Serre, it says that if you work with elliptic curves, which are non-CM, which means that if you look at their endomorphisms not just over K, but over K bar, and this is important, you can just get Z. Okay? It's really important to put K bar here, because there's lots of examples of curves where they have no endomorphisms over Q, say, whatever quadratic extension, you get an isomorphism. And then that limits the Galois group image over the quadratic extension, but that's just a finite step away from the full Galois group image. So it's important to look at the isomorphisms over finite extensions as well. Now, okay, but so if this is the case, then the image of the adelic image of the Galois group inside GL2Z hat is open, and in particular, and thus finite index. Okay. Good question. So note that Tate's theorem, in this case, Falting's theorem, tells you that for every prime P, the image in GL2ZP is open. Just sort of study the possible group images. But this is stronger, because in theory you could have sort of a different, a deeper index at every prime, or even index 2 at every prime, and that wouldn't imply this. So together you get infinite index. Okay? So this is really a stronger theorem. All right, so we don't have anything like this in general for abelian varieties, although we expect something like this, though more complicated. The group theory becomes more complicated. But we do have the following theorem, which sort of comes a little close. Due to Winterberger, which says, okay, we can't get sort of finite index in general, but we can get something, at least some sort of very weak form of uniformity. So it says the following. So if you have, again, let's go back to A over K in abelian variety. Then it says there exists an M bigger than 0, which I think maybe is even uniform in the dimension in K. I'm not sure, but he doesn't claim this, so I haven't come to the proof. But there exists a positive integer M such that if you look at the adelic image of phi A, at the very least, it contains not quite the full center, but it contains the nth power of the center. Okay? So again, it follows from Tate's theorem that for every P you contain some open index subgroup of ZB star, which contains some power of ZB star, some power of it. This is saying that they power uniformly over all primes. Okay? And this is not, of course, stronger than Falting's theorem or anything. It only talks about the center. It is something a little bit different. Okay, so this is actually all we'll use in our proof of London offered. This thing. There's much more to the story of sort of Galois actions on Tate modules and on the adelic completion, but we won't go into that.
So
yes.
So there's also this kind of weight pairing going on, right?
Yes, there is.
Kind of, but that you don't see that, like, you can have some sort of determinant condition, right? Or,
yeah.
You have to preserve this symplectic form, but you don't see that on the whole. Like, it might force your index.
Are you saying how does the weight pairing jive with this?
Yeah.
I don't know offhand. So the weight pairing does tell you what your determinant image is, essentially. So then you have to be a little careful, right? Because having things in the center, like something being in the center, certainly implies your determinant image at least contains like the, whatever, 2gf power of this. But vice versa is not quite true. you can have large determinant image with much smaller center. Does that make sense?
Yeah.
So I think dealing with that causality is largely what Winter was doing. I feel like I didn't answer your question, maybe.
No, yeah. That helps, yeah.
Okay. All right.
I mean, first, like, in the elliptic curve case, like, because of that vapor, you actually get, like, index at least 2. Somehow it forces, like, you have to contain the...
Why do you get index at least 2?
Because I think you have to contain the square root of the discriminant or something like that. Like, there's some Galois condition, like, because you have to contain a cyclotomic field that you...
Yeah, I guess I'm not sure exactly about the interval. I can't immediately see any implications one way or the other.
Like, I think it's because of the 2 torsion.
Uh-huh.
So then you're looking at...
What you're talking about is there is... So, okay, going deeper than I am comfortable going. I know that... So, David Zubin understands this really well. He has these papers about the image, on average, being as large as possible. And yeah, if you're over Q, for example, you're always at least index 2, I know. Because there is some sort of matchup between the action on the 2 torsion and the determinant. Somehow there's some correspondence there, which might be what you're talking about.
Yeah, like in the elliptic curve, like the 2 torsion, like you're joining, like if you're joining that field, you're joining like a square root of the discriminant.
Right.
But that's then contained in some cyclotomic field.
Right.
And because that's like that force.
And then that with the vaporing, the determinant creates conditions. That's right. Yes. That's true. I'm not sure exactly how it relates to this though, right? Because I'm not sure that limitation on containing elements in the center. Yeah, they might be, but I just can't see the relation right now. Cool. All right. Okay, so we're going to use this theorem in the following way. So let me call this theorem 1. You would be able to refer to it. Okay, so we're going to have a theorem purely about equidistribution now, which is the following. So let Si be finite subsets in some power of Q mod Z, which we think of as sitting inside some power of R mod Z. So these guys are finite sets. So of torsion point, which are also Z hat star to the M orbits. Okay? So to make this precise, to clarify what I'm saying here, so Z hat star actually just acts on Q mod Z, right? I mean, ZP acts on QP mod ZP, just by multiplication, and ZP star acts as automorphism of QP mod ZP. And so, putting that all together, Z hat star acts on Q mod Z. This is some subgroup of Z hat star, so that also acts on Q mod Z. And so it acts on Q mod Z to the N, just by the product. And so these are finite sets, which are single orbits under the Z hat star to the N. Okay? So maybe it might make it easier to think about if, so if M equals 1, and you identify Q mod Z to the N with the roots of unity in C star to the N, then this is exactly the Galois group action on N tuples of roots of unity in C star to the N. Okay? All right. Questions? Okay, move on. Okay. Okay, so S are finite sets, which are orbits under this. And of course, the reason this is natural to consider is because that's exactly what we're learning here, right? I mean, Galois group action somehow is, in general, is very complicated, but we know how the center acts. It acts exactly in this way. And the torsion points abstractly, just sitting inside the closed Lie group, are Q mod Z to the 2G, sitting inside R mod Z to the 2G, and we know they're stable under this action. Okay, which leads us to consider these orbits. All right, so suppose these are finite subsets. And also suppose that if we look at the associated measures, I guess I called these delta SI before, right? So suppose that the measures delta SI, which again are the averages of the point masses, converge, as always in the weak star topology, to some measure mu. Okay. Okay, then there is a finite union of torsion cosets. Let me call it T. Union of these torsion cosets T sub I, such that mu is the Haar measure associated to T, but what should just mean is the average of the Haar measures associated to each of these torsion cosets. Equals 1 over n. Okay. So what's one sort of degenerate case of this happening, or it's actually a fairly general case, it just looks degenerate. But one such case is that SI are all and the same, they're all just a single sort of finite set, which is an orbit of Z hat star to the M, and that's still finitely many points. And so in that case, this T is just a union of finitely many points. This mu is just their average. Okay? All right, so before proving this theorem, it's just a theorem about equidistribution, asked, character sum, whatever. Let me first prove that this theorem, theorem 1, implies the Riemann-Mumford conjecture. Okay? It's a proof of this. All right. So suppose that, again, A has been a variety over K. V inside A is some subvariety. So we're going to prove this by contradiction. Then you can probably set this up to be a constructive proof, but it's easier to set it up this way. So assume Riemann-Mumford is false, and then let T1, T2, Tr, so forth, let these guys be the maximal torsion cosets here it's in the abelian variety sense, not just with real Lie groups, inside V. Okay? So now the idea is again to pick some sequence of torsion points in which to apply this theorem and then to get some sort of conjugation. Okay, so how do we do that? Okay, so what we do is pick a sequence T1, Tr, so forth, of torsion points. in V such that if you look at the ith torsion point, it's not in the union of the first I torsion cosets. Okay, so eventually the sequence jumps out of any finite union. Which you can do, of course, because if you couldn't do this, well, then this would be all of them, but we know that there's more. Okay? Okay, and then let Si, so let these be these torsion points. Yes. And so let Si be some subsequence of T, so T sub K sub I. Such that if you look at the delta measure associated to the Galois orbits of this, then this converges in the weak star topology to some measure. Converges to mu. Where what are the SIs? Well, I could take the SIs to be the full Galois orbit, but I'm only going to use the center anyways. So I'm really going to just take the SIs to be the Z hat star to the M orbit of little si. Okay? Oh, I'm sorry. I forgot an important additional conclusion here. Sorry, a minor. I wrote it down, but I forgot to say. Yeah, so it converted to some measure T, and there's one other thing we need, so such that this, and for all sufficiently large I, these T's actually contain our sets S sub I. Sorry. One second. Yes.
I think we can make the TIs to be disjoint.
Are we over here?
I guess even from the beginning, the TIs
Yes.
will be disjoint.
No, they're disjoint.
So then you're just defining mu T to be that. It's not going to be. Okay. It's just like does mu T equal the average?
So mu T is a measure, right?
This is by definition. Right?
This is by definition, yes.
Okay.
Sorry. Yeah, this is the definition of mu T.
Okay.
So for a single torsion course, I just mean the Haar measure.
But you're going to double count some points.
Well, this is a measure, right? It's not a set. So we can always average measures. Right? I mean, what's a measure? A measure just tells how to integrate any function.
Yeah.
And so I'm just saying to integrate any function against this measure,
Yeah.
what I do is just integrate it against these measures and divide by n.
Okay.
Yeah, sorry. So this is important. Sorry, so going back here, yeah, so we have our maximal torsion courses, infinitely by assumption, take a sequence of points to eventually jump out of all of them, and then take a subsequence such that the Galois orbits converge in the weak star topology. Note that the Abelian variables are compact, so in some sense it's easier. We don't have to worry about escape of mass like we did for the GM case. We know that some subsequence of these measures by weak star compactness will converge to some probability measure. Okay? Great. Okay, so now we apply theorem 1. So then by theorem 1, I gotta use different notation now. Let me call these, I don't know, WIs, I guess. There exists torsion cosets W1 through some WR, such that mu is the average of the Haar measures associated to these torsion cosets. And for all I large enough, the SIs, the little ones or the big ones, let's say just the little ones, are contained inside the union of these guys. So,
Okay.
okay, so now note a couple things. So, since the SIs are dense in the union of these guys, they have to be for the measure to converge here. It follows that this union is contained inside V. It's all of our points over V to begin with, and they're dense inside Wj, and these are both closed. Okay? All of these guys are in V. Okay, but these guys are torsion cosets, and we know that the T's were the maximal torsion cosets. So each one of those is contained in one of these. Okay? And so therefore, it follows that this union is contained inside some union of the T's, up to some big M, say. Okay? Okay, but this is a contradiction. Because we know that for sufficiently large I, the SIs are contained inside here, and they're not contained inside here, because they were picked to eventually jump out of a finite union. Okay? Questions? All right. Okay. So now let's go right distribution statement. And so this really hinges on the one-dimensional case, just like it did in the roots of unity setting in the GM setting, because we mentioned we're going to take characters that will reduce us to being inside the one-dimensional case. So let's start with that case. So suppose you have T in Q mod Z, and that capital T in Z hat star E M dot little t. So what we need really is, well, we call it theorem 2. Theorem 2, which says that as the size of capital T goes to infinity, the associated measure converges to the Haar measure on S1, so on R mod Z. Okay? Okay, so let me give a proof of theorem 2 implies theorem 1 first. Well, eventually you have to actually compute some like Gauss sum and do a little bit of analysis. I'm just saving that for the very end. I'm doing all the legwork first so that we can get that out of the way. I don't know, I find it confusing to think about analysis in high dimensions, but when it's a single sum, it's much easier. Alright, so let's prove that this implies theorem 1. So how do we state theorem 1? Right, so, okay, so recall, so we have some sequence, so Si and Q mod Z to the N, which sits inside R mod Z to the N, all of which are orbits under Z hat star to the N, and we're assuming the delta measures converge to some set mu. Okay? That's sort of the setup. And we want to prove that mu is associated with finite formating torsional cosines. Okay, so we're going to split up into two cases. The cases will essentially be either you're fully equidistributed, mu is just all of R mod Z to the N, mu R mod Z to the N is just Haar measure, or you're going to lie inside some finite set of torsion cosets. Case 1. Case 1. Yeah, put a bracket. Looks nice. Okay, so case 1 is for all characters chi from R mod Z to the N to, to R mod Z. I mean, normally characters go to S1 multiplicatively, I'll just write it as R mod Z additively. So, for all characters like this, the size of chi Si is unbounded. Okay? Okay, now as was the case for the GM case, Z hat star to the M acts both here and here, and it acts compatibly. So if you map on a single Z hat star to the M orbit here, you get a single such orbit over here. Right? Now in this case, so since this is unbounded, so since this is unbounded, and the single Z hat star to the M orbit we know that this measure converges to Haar measure, mu R mod Z. Okay? And what is this really saying? Well, another way of saying this is that the integral of the character chi with respect to the measure mu is equal to 0. What it means for this to be equidistributed. Okay? Because again, the intermediate step is that this guy here is is literally equal to the integral of e to the power of 2 pi I t d mu of t is equal to 0 because mu is Haar measure. So these claims are exactly the same. All right, but so if all non-trivial characters chi integrate to 0, that means that you're Haar measure by the scalar Milton theorem. So that means that mu equals Haar measure. Okay, that's case 1. Right? Okay. Let me go. So what does case 2 say? Case 2 says for some chi, chi of Si is bounded. Right? But these guys, I mean, these sets equidistribute. So these are a sequence of finite sets, which means they eventually just have to be constant. There's no other choice. Thus, chi of Si is actually constant. For large enough. Okay. Another way to see it is there's a sort of, these are z has started the m orbits, and those get larger and larger. There's only finitely many orbits this can be. You can't iterate between them. You can't sort of be in different sets. These are equidistributed. So this guy is eventually constant, which means, i.e., there is actually some constant set. So call this set S. So that means that for I big enough, the S sub i's lie inside chi inverse of S. And what is this? This is a finite union of torsion cosets. I equals 1 to whatever size of S of some torsion coset of smaller dimension. Okay? Now by induction, in each one of these will become equidistributed, and the z hat star to the n permutes us between them, and so that completes the proof. Okay? Now by induction, for each j, Si intersect Tj becomes equidistributed in some finite unit torsion cosets. And so then z has started the m permutes them between different components, and so you're that many more torsion cosets. It's what all of Si is equidistributed. Okay. All right. So we really reduce to the one-dimensional case. Okay. This is also the benefit of phrasing it somehow just as orbits of a single group z has started the m, because the induction sort of works that much easier. In terms of working with a full Galois orbit, it would be hard to set up the induction property. Okay. Okay, so now we need to talk briefly about Gauss. Now we're in the one-dimensional case. We have to do some actual analysis. So it's all built on the following lemma. So let P be a prime. And chi from FP star to C star be a non-trivial multiplicative character. Okay. And E C star be the additive character. It can be any additive character, but we'll just take it to be the usual one. E of A equals E to the 2 pi I A over P, lifting A to 0. Anyway. Okay. Then if you look at this sum, chi of A, E of A, and F B star. So we're summing roughly P elements, P minus 1 elements, and the size of the sum is roughly root P. Okay. We're going to be summing along multiplicative subgroups, we had started the M, and so these sort of character sums are essential to picking out sort of getting equidistribution results. So we'll need more than just primes to begin with, to finish, but to begin with, this is not the main case. So the proof is quite simple, or quite standard, I guess. What we're going to do is compute the square, the norm of this guy. So this is just this guy times its conjugate. Now the conjugate of a root of unity is its inverse, and so I'm going to rewrite this. Is like this. Okay. And now we do a change of variables, where A is B times C. This is a sum over A over B and C of chi of C, E of B times C minus 1. And so we these are both in F star. So now we execute the B sum first, because that's only in the additive world. And what is this equal to? Well, whenever C is not equal to 1, we get a complete sum over FB star, which is equal to minus 1. Because if you add all of them, you get 0. We're just missing 1. So if C is not equal to 1, you just get minus 1. And then if C is equal to 1, we're just summing 1 P minus 1 times. Then we get P minus 1. Okay? And likewise now this is a multiplicative character. So if we were summing this over all of F star, we would get 0, but we're missing 1. That's minus 1 with a negative here, so we get plus 1. That's equals B. Okay. Sorry, it's a standard computation, but if you haven't seen it before, you should see it once, at least. Okay. Now that it looks quite simple, but sort of, if you remove the F value and just square it and do the same trick, it becomes much harder. It's not it's worth trying. Then you get a Tsimerman sum, and it's much harder for good reason, because the answer isn't P, the answer is something subtle. All right, so this is already sort of, this is enough to handle the case where T is sort of just P power, as we'll see. It's just P torsion for P getting larger and larger. Next time, okay, at the beginning of class next time, we'll finish the proof of distribution. So,